This is section 3.6 of the chain rule, derivative technique called the chain rule. So the chain rule basically is dealing with derivatives of composite functions. And on the first page of notes, we're going to review some of these composite functions. When you think of a composite function, most people think y equals f of g of x. And to give a couple examples of those, let's consider y equals the square root of x squared plus 2x. So if that's the case, we'll have a y equals f of x and a g of x. So f of x would be the outermost function, which is here the square root of x. And g of x is the inner function, which is x squared plus 2x. You see, if I wanted f of g of x, I would take this g and plug it into x of f, and that would yield this function here, y equals f of g of x. Another example might be y is the cosine of 5x to the power of 7. In this case, our f of x is the sine of x, and g of x is the inside stuff, which is 5x to the power of 7. These composite functions can extend to ones of f of g of h of x, one embedded into the other. An example of this might be y equals the sine of quantity 5x squared minus 1 to the power of 8, like that. In this case, our f of x is the outer function of sine x. G of x would be x to the power of 8, and finally h of x would be 5x squared minus 1. The final example, y equals the secant squared of 2x plus 1. You got to be really careful before defining f, g, and h here. This notation with the squared, really what it means is the secant of 2x plus 1 is all being raised to the second power. If you write it like this, it is easier to identify f, g, and h. So now f of x is x squared, g of x becomes the secant of x, and finally h of x is equal to the 2x plus 1. Now the bottom of the page 1 of notes describes a little bit about the chain rule, but I think it's best to understand the chain rule through examples. So that's where we're going to go next. Lesson 3 examples. Number 1, consider y equals the square root of x squared plus 1, and our goal is to find dy dx, the derivative. But before we do that, we're going to write this a little bit differently. We're going to say x squared plus 1, and we're going to raise that to the 1/2 power. Now I'm about to say something that might drive you absolutely insane, but I really think it helps. And the thing I'm going to say today, a ton, is the word stuff. So if you were in class, I would instruct you to not call this quantity x squared plus 1 to the power of 1/2. I would instruct you to call this stuff to the 1/2 power. So now we're going to find dy dx. What is the derivative of stuff to the 1/2 power? Well, looks like we're going to employ the power rule. So I'll bring down the 1/2. Then I have my stuff, and that stuff will be now raised to the negative 1/2 power. So here's where the chain rule comes in. If I'm using the word stuff, then it's 1/2 stuff to the negative 1/2, and then the chain rule ends by taking the derivative of the stuff. So the derivative of stuff is simply 2x. We're going to leave it unsimplified so that we can see the pieces of the chain rule. Number 2, let's define f of x equal to the quantity x to the power 5 minus 4x plus 8, and that will be raised to the power of 7. If you were in class, you would call this stuff to the power of 7. So now when we find the derivative, using Lagrange notation, stuff to the power of 7, its derivative is 7. Stuff to the power of 6. And then I have to remember to multiply by the derivative of the stuff. And I'll use parentheses here, 5x to the power of 4 minus 4. I'll use parentheses so that I am multiplying by the entire derivative of stuff and not just part of it. Example number 3. F of x equals 1 over the quantity 4x squared plus 6x minus 7, and that quantity is raised to the power of 3. If we can use the power rule, we're going to be a lot more happier because it's a simpler process. So I'm going to write it as 4x squared plus 6x minus 7 to the negative third power, or stuff to the negative third power. Now we'll take our derivative, f prime of x, power rule, negative 3, stuff to the negative fourth power. Now I'm going to multiply by the derivative of the stuff, 8x plus 6. As soon as you say the words derivative of stuff, we stop. I don't now want to take the derivative of stuff. I want to stop with the derivative of stuff. Example number 4. There's an overarching principle or property to this one. I hope that you can see it. In this one, we have a product. So the overarching property that we will use is the product rule. Okay, so dy dx is what we are going to find using that product rule. So it's the first term times the derivative of the second. But be careful, when we take the derivative of the second, it is going to be some stuff to the power of 4. So the derivative is going to be 4 stuff to the power of 3. Now I need to take the derivative of that stuff, which is simply 3. Be careful, this little guy illustrates the chain rule. It needs to be there, it's very important. Next, I'm going to plus the second term, which is 3x minus 1 to the power of 4, and I have to multiply it by the derivative of the first term, which also is a composite function, stuff to the power of 3. So we have 3 stuff to the power of 2 times the derivative of its stuff, which is 2. Again, these guys here represent the chain rule. Please note that I would like you to keep this unsimplified for now so that we can see the pieces, we can see where we made our mistakes. Of course, the 4 and the 3 together would make 12, and the 3 and the 2 together would make 6, but for now, let's just leave it like this. Example number 5. F of x equals the quantity 7x plus, let me throw a little trig in there, cosine of x, and that's raised to the power of 4. And then we're going to multiply that quantity by 3x squared minus 1 over x, and that quantity will be raised to the power of 3. I would like you to find f prime of x. Best case scenario here, press pause, try to work it out, then when you unpause, you can check your solution. Press pause now. Solution revealed. Let's walk through it. And the yellow will be my first term, and in the blue will be my second term. Okay, so that means I have first term, and then when I do the derivative of the second term, it's stuff to the power of 3. So here we have 3 stuff to the power of 2. Now the second part here is the derivative of the stuff. If you recall, I took this quantity here, did it in my mind, but I wrote it as x to the negative 1 power so that I could use the power rule. So again, when I take the derivative of stuff, it's going to be the derivative of this, which is my 6x, and then minus the derivative of this, and the derivative of that turns out to be negative 1, x to the negative 2 power. This negative here, together with the original minus, is why I have the plus. That finishes the first term times the derivative of the second. Now I take the second term and I multiply it by the derivative of the first, and the first is stuff to the power of 4. So I have 4 stuff to the power of 3, and then times the derivative of the stuff. Let's review that. The derivative of this term is 7, and the derivative of this term is negative sine x. Hopefully you got that one right. The next problem is considered a challenge problem, not because it's harder or longer, just because it's a little bit more tricky. F of x is the square root of x plus the quantity x to the power of 4 minus 2x, and then this local quantity is raised to the power of 7. Let's do this one together. F prime of x, the derivative. Of course, you see that this is a bunch of stuff raised to the power of 1/2. So we're going to start off with 1/2 the bunch of stuff raised to the negative 1/2 power. Now I'm ready to multiply by the derivative of the stuff. But check this out. The stuff is comprised of two parts, the x and then the other term, which is here. So to find the derivative of the stuff, I have to take the derivative of each one of those separately. The derivative of x is 1, and then we're going to add the derivative of the quantity that's underlined in light purple. And that quantity, that local quantity, is a composite function. And if I'm taking the derivative of it, I will use the chain rule. And that will be stuff to the power of 7. So 7 stuff to the power of 6 times the derivative of stuff, 4x cubed minus 2. This, again, purple quantity, the light purple quantity, all of that was the derivative of this part here. Now I'm going to close off these parentheses here, which represented the derivative of the entire radicand, that original stuff. Example 7, the last one before we work with some more difficult trig functions. Let's do 5x squared plus the quantity 2x cubed minus x raised to the power of 5, and then the entire quantity is raised to the power of 7. I would like you to press pause and then check your solution. So press pause now. Solution revealed. 7 stuff to the power of 6. And then inside we have two different parts of the derivative. We have the derivative of the first, which is 10x, and then we have the derivative of the second part, which I'll put a double underline, and a double underline was the derivative of this part, which in and of itself was stuff to the power of 5. 5 stuff to the power of 4 times the derivative of its local stuff.